Well, I was asked to come and talk to you all about the connection between rocks and plants. And the question is, when you find a plant, I always think, well, why is this plant here and not somewhere else? Because you do have these plant communities, and you'll go out and you'll see plants that are growing together. You move to another place and you have another group of plants and another community. So it started originally with when I was a student of geology at New Paltz. This is upstate New York, southeastern New York, and I was given 1 square mile of area here to map the structure. It was structural geology. Do you see any rocks? Yeah, it's a real challenge, but that's where I did my undergraduate work, and that's what they sent me out to do. This area has a lot of very complicated structure. You can see these white streaks here. Those are rocks. So, how did I work this? Well, this is one of my friends. Yeah, go ahead. Now, when you get poison ivy, and I got it really early, I had to know this plant very well. I learned it very, very well, and was always on the lookout for it. Lived in New Jersey. There were places where it was really, really bad. I remember my father taking me to this one place to collect minerals. And there were bushes that were just enormous. And it was coming out of the trees. Just so much of it. Where I lived, the house, there was very little. Then I moved to upstate New York. And that was in Oneonta, which I didn't know at the time, but that's the Catskill Delta. Big, ancient delta, sandstones. No poison ivy at all, except down in the Susquehanna River, they had a spillway dam, and it grew all around that dam. Then I went to my undergraduate, and there were places that were just full of horrible amounts. And I started doing these little mapping jobs. I began to realize if the poison ivy was about this high, you were probably in the marine shales. If it was this high, it was the limestones. And if you were in the sandstones, you didn't see it at all. So that was one of the things that I was using on that mapping project. I could go out and map using poison ivy alone. Next slide. This is one of my really great friends. I discovered this one while I was doing the project. This is the eastern red cedar, and it grows on very shallow soils or rock. You can see it growing on the rock outcrop here and how shallow the soil is there. Well, what I would do is, after realizing this, I could get up on a ridge and look out over my area where we were going to map. And it usually grew on the Martinsburg Shale, which was the lower part of this. And I could say, I'm going over there because there's going to be an outcrop there, there's going to be an outcrop there, there. And when I would go there, sure enough, there would be places where the rock would come to the surface. And one of the things we were trying to do with this structural geology course was use our techniques. We would go up, and this shale had both bedding and cleavage. So we'd measure the direction of the cleavage and measure the direction of the bedding with our little Bruntons compasses. And then you plotted it on this thing, and it would tell you what the structure was, even though you couldn't see the entire structure. You were just seeing little spots. And by doing it and using this plant to find all the outcrops, I was able to find out there was this huge recumbent anticline, this big fold that had fallen over sideways, came out on our plots just beautifully. So the next plant we had, next slide, I was going along the ridge and I found this. Eastern hemlock grows where it's cold. Why is this growing here? Well, I continued down along the ridge and I started noticing that the cracks in this big sandstone were getting bigger, wider, and wider. And I was getting more and more of this. Turned out I was going into an area where the whole conglomerate, which is a couple 100 feet thick, was broken by the glacier and opened up as big cracks in the ground. The snow would then fall in there in the winter and it would be trapped, and it would stay in there all summer long. They were called ice caves. And if you ever go to this part of the New York State, near Ellenburg, they have a tourist trap to go in, go down in the ice caves and see these piles of snow. Well, me and my partner look at this and go, that time, the drinking age was 18, so I was over 18, we could buy beer. Our professors are going to come out and do a field check on us. So we took a 6-pack of beer, stuffed it down in the ice cave, and when the trip came, when the professor came to check us out, we took him around, showed him our sites, and talked about it, and walked around, pulled out a nice cold beer. Needless to say, my partner and I got an A. A real memorable project. But these plants really helped me out. And there were several others that were also helpful. So next slide. So now, why did this all occur? What is the connection between rocks and minerals? Well, first of all, we need to know what a rock and a mineral are. So, the definition of a rock, it's a combination of one or more minerals. Okay, what's a mineral? Well, it's a naturally occurring crystalline solid with a definite chemical composition or one that varies within predictable, easily defined limits. So next slide. Well, here are some minerals. Yes, ice is a mineral. Not as water because it's not a solid. But once it freezes, naturally occurring, crystalline solid with a definite composition. Salt, also a mineral, called a halite. We have mineral names for every compound. The interesting thing about ice, of course, is that if you get a pile enough, deep enough, it starts to flow out on itself in a solid form called a glacier and just spreads out. Salt does the same thing, but it needs more pressure. We don't see that very often because most salt dissolves away where it rains. So if you go out to a place where it doesn't rain, like the Iranian desert, there's a place where a salt dome comes up as a diapir, comes up into the surface, and flows downhill under its own weight. Okay, there's a continuum of those. The next one, of course, is the serpentinite minerals. And you always see serpentinite squeezed up through faults. Well, that's why. It's also can act like a toothpaste, but under higher pressure. Next one is silicon dioxide, quartz, very important mineral. And the next one is feldspar. This is potassium feldspar. Feldspars are, by the way, the most common mineral in the Earth's crust. Lots of feldspar. So next slide. I think you just went backwards.
Oh, sorry about that.
Go the other way. There we go. Okay. When I said crystalline type, crystalline is the arrangement of the atoms, and they're in a regular order, and it really makes a difference what that order is. So like if you have carbon, you can have two very distinctly different things, diamonds and graphite. Graphite is dark, opaque, slippery, very soft. Diamond, clear, hard, hardest substance, natural substance known. Silicon dioxide can be 4 different minerals depending on the pressure and temperature at which it formed. And same thing with the K feldspars. There's 2 different kinds. There are actually several more besides that, but those are the 2 most common. Now, the reason I'm talking about this is each one of these is going to react differently in soils and in weathering. So it's important to know what rock has which ones, because they are distinct, different compounds with different ways of reacting. Next. So what do they do for plants? Well, the rock, if it doesn't have any way of getting the soil other than weathering, it determines the soil type at that location. It also determines the available minerals, and by minerals here I'm talking about what kinds of chemical compounds the plant can take up, like copper, calcium, what form they are, whether the plant can really dissolve them and bring them into the plant. The rock can form structures that the plant can use. And by that I mean fractures, places where the roots can go down. It can take cliffs, which will give shade, or hills. Water availability. Rocks, of course, have pores, cracks, and so on. And depending on how the rocks have those, you can have springs. You can have places where it drains out very easily or where it pools up. And of course, aspects and slope are very important for any plant. And normally those are caused by resistant rocks, which form hills, or easily eroded rocks, which will produce valleys. Next, please. Okay, so we're talking about these elements that plants need, and here are the 10 most abundant elements in the Earth's crust. 10 most abundant come out to 99% of the Earth's crust. And the next slide, those are the ones that plant life depends on. You'll notice that there's only 6 of them that it really depends on. These are useful for plants, but are not required. Plants can use those, like silica, grasses can use silica to make them somewhat impalatable, but it doesn't need it to survive. Next, please. So now we're talking about the big 3 elements, the ones that you see on a fertilizer bag. If you don't have these, plants are really not going to do well. N for nitrogen, P for phosphorus, and K for potassium. Now you would have noticed if you go back to that slide before, there's only one of those. It's in the top 10. And that's potassium at number 7, which is only 2.6% of the Earth's crust. So where are the other ones? Go ahead again. Next. Well, nitrogen is almost entirely in the atmosphere. You look at the crust and it's 0.004% of the crust, but it's 78.1% of our atmosphere. You notice carbon wasn't in the top 10 either. Carbon is 0.32% of the crust, and now, and going up, 0.04% of the atmosphere. Funny that it used to be that the atmosphere had less percentage carbon than the crust, and now it's reversed. Number 11, by the way, in the most abundant is phosphorus, which is one of the big 3. Now we have nitrogen, phosphorus, and potassium are taken care of. The rest of these are other essential elements for plants. And you notice the percentages get very, very small. And each rock type contains different amounts of these. And since they are essential, and you know the rocks are going to have different amounts, you can start to see why different plants might be in different places. They won't, each one of them is evolved to need certain amounts of these. So the next slide, please. Here's what they do. Of course, carbon, oxygen, and hydrogen, they make up the major components. You don't get a sugar or a carbohydrate or a wood or any of that without those 3. Nitrogen makes all the proteins. If you don't have proteins, you don't have life. Potassium, it's an interesting factor in many, it's what the plant uses to balance its water solute function and even operate its stomata. It's a very important thing. So that's why nitrogen, potassium, and phosphorus are so important. Phosphorus, by the way, down here, it's in the nucleic acids. It's the energy transfer. If you remember back to your thing, ADP and ATP, adenosine triphosphate and adenosine diphosphate, that's how all the energy takes place. And we see some of these others. I thought it was interesting to note that potassium doesn't do it, but copper, is copper? Yeah, copper. It's very important lignin, for lignin biosynthesis. So if you don't have copper, you can't make wood. And zinc, important in the formation of chlorophyll. Who would have thought? You know, some of these things are really interesting needs that plants have. So next slide. So these are some of the rock types we see around here in the Franciscan complex. They are the most common ones: the Chirp, the greenstone, the serpentonite, and the greywacke. And I want you to look at serpentonite. No calcium. No potassium. And phosphorus, they couldn't detect that either. So you're looking at a soil that for two of the three major components that plants need doesn't have very much. It's below their detection in this thing, which was taking it down to 1/10%. And that means that life, or the plant life, is not going to do very well in a serpentinite like that. It also means that the nitrogen will not be there, because to get nitrogen you really need a lot of biological processes. And then you're not going to get the plants to grow, you're not going to get the rest of the biology. Greenstone is one of the more interesting ones. It has a good, fairly good potassium level, good calcium, magnesium ratio, has a nice amount of iron, has enough silica to form a soil, has a fair bit of phosphorus. So greenstones are one of our better places for looking for plants in the Franciscan. Greywackes are also pretty good. Chirps are a little bit depleted. So when you go out and start thinking about where you're going to find the greater diversity of plants, greenstones are some of your best ones. Greywackes aren't too bad. Serpentines, they're going to have the rare ones, the ones that can handle very, very tough conditions. So the rare, unusual plants will be in the serpentinites. The greenstones will have the more common plants and more of them. So next slide. Okay. Plants do not grow on solid rock. Why is that? Because there's no place for them to get their roots in. And this is a little parvacetum that took a shot on top of a basalt flow. Now what is happening here is you can see where the weathering is occurring, fractures. And so soil is developing in there, and that's what it's taking advantage of. And since it's such a poor competitor based on sunlight, this is where it likes to grow. Has enough soil and the sunlight to be happy. So next one. So what are soils? Well, they're the things that are remaining after physical and chemical weathering of the rocks. Obviously, things that remain in soil cannot further oxidize. If you oxidize, they've changed. They do not dissolve. If we had minerals that dissolve, they're not going to be left in the soil. And they're resistant to all sorts of soil chemicals, like the acids from plants and the decay, fungi, and so on. So the common things that you end up with soils around here are essentially quartz and clay. And quartz is just very resistant to most acids. It does dissolve, but it dissolves slowly in our climate. If you get down to the tropics, it dissolves too. And eventually you end up with what's called a laterite, and it's all aluminum oxides and iron oxides. Very, very depleted soil. That's when the clay minerals even break down. Okay, each rock type will give you a different mix of grain sizes. If anybody else gone up to a granite, you'll see sometimes that the crystals in it are really big and other times they're really fine. So when they break down, those grain sizes are going to affect how the soil is going to be, what kind of texture it is, and the types of clay minerals are going to be from what minerals are breaking down to produce those clay minerals. And a true soil is not just the breakdown products, it develops a structure. So if you've ever heard about the A, B, and C layers, those structures do exist out there in nature, and they are important because living things actually segregate themselves in those different layers. And it's very important, and if you disturb it, you can ruin the soil for a long time for the plants that need that structure, that have to have that community in there. So next. And here's a clay mineral. Now what's important about a clay mineral? It's a layer of silica, a layer of aluminum or magnesium oxides, another layer of silica, and between the silica layers is this exchangeable cation layer. So if you think about all those things like potassium, phosphorus that are going to be soluble, the clays give a place for them to stick. If you don't have biological places for reservoirs for those elements, this is where they go, is in clays. That's why sandy soils tend to be poor areas for plants. A little bit of clay is good. Too much clay, of course, you end up with it being too fine-grained and the water doesn't move. It kind of closes off the water flow and the oxygen which the plants need. So the best thing is clays mixed with sands, mixed with silt in a ratio of about equal amounts, and that gives you the best things. They're called loams. They have the exchangeable ions, they've got the drainage, the oxygen availability, because they're porous enough, and they allow water to come in. Okay, next. Okay, this is Edgewood, and this is a picture of the central ridge, and what I'm showing here is the serpentinites are located here. Up here on the top is a greenstone. Now the serpentinites do not support any shrubby plants down here. It's all grassland and forbs. But you'll notice that the contact up here where the serpentinite and the greenstone come together, about up in here, but you'll see these lobes of plants coming down. This is a mixed soil. And mixing occurs because of gravity. You know, the soils that are produced up here slowly, make their way down the hill. And at Edgewood, you get these great places where it comes down into a swale, and you'll have shrubs and certain plants, even weeds, on one side. You get to the swale, you go up the other side, and suddenly you don't have those anymore, because this was all derived from serpentinite, doesn't have the potassium, doesn't have the phosphorus that were coming off the greenstone, and now they can't grow. And it's like drawing a line. We've had a couple places, unfortunately we pulled all the yellow star. We would see yellow star on one side of a little swale and on the other side none. And it was because both sides may have had serpentinite, but one side had greenstone that would flow down, mix in the soil, and made it available to grow the yellow star. And we still have some plants like that, but it's not as obvious. Next, please. The serpentinite is kind of like a pudding. It has little chunks of other rocks all through it. And here is a chunk of another rock type out in the serpentinite. See all around here, the native grasses and the hayfield tar plant. This is one coast live oak. Around the coast live oak, there are a ring of coffee berries, and then this lower stuff here is leather oaks. So what we're seeing is the rock in the center is one which will support a regular tree. It's probably a greenstone, could be a chirp. I didn't really be able to see this because it's such a small island. As you get away from that, you start mixing with the serpentinite, and it then becomes to the point where the leather oak can grow. And then you get out here, and neither one of them can grow. The thing about serpentinites is they tend not to support very many woody plants, and these are woody plants. The next one will show you, oh, too far. Should have been one back there. This one. This is that same island, and we're looking at the bottom part of it. And you'll notice that the leather oak is flowing out downhill, just as you would expect if the soil was eroding down and changing the serpentinite below it. And you can see other islands. This area out here in the Clarkia is really fascinating because there are several blocks of material that look like they were taken down and broken up, and they actually form a linear pattern, and you can follow these linear patterns across it and find different plants that are found on those linear sections. We used to have a place where they had planted eucalyptus across Edgewood, and it lined up on a edge of a schoolhouse that they put a windbreak around, and you could line those eucalyptus right up. But they only survived in these two locations across the serpentinite. And it turns out that those, if you intersect them and follow them back, you would find the lozenges, and there was a Erythronium, and another place where there was, I forget what the other plant was, but you know, you'd look at them and say, well, these are slightly different plants that were running that, and they come right to this point where they planted the eucalyptus, and the eucalyptus survived on this little ridge or little line going across. So next slide. This is Rosinweed, and this was reported to be in Edgewood, but we have not found it. Now Edgewood, when they were doing the original surveys, was a lot bigger piece of serpentinite than it is today. So it might have been just outside somewhere and that area was destroyed. But at Jasper Ridge they have this, and they also have it on the trail coming down from Los Trencos Woods to Foothill Park. And the interesting thing about it is at Jasper Ridge there's a strip going across the serpentinite where this is abundant. And all of a sudden you'll get to the point, and on the both sides it just stops. It doesn't look like the soil changes, but something makes this grow in one part of the serpentinite and not the other. And it's abundant where it is. And these are sort of mysteries of serpentinite because these streaks seem to be common. Just a change in the chemical composition. It could be very minor because what you're looking at with these serpentinites is that you're digesting blocks of rock that have been pushed down into the earth, and as those elements that were in the original rock, you know, bleed out of the original thing, you end up with these bands. One of the bands they have there is very interesting. There's a gold field, and there's a little line, and on one side it's one type of gold field, and on the other side is another, and you can only tell them very, I forget what the method is, they can tell them apart, but they're genetically different. And yet, right there, the line. Next one, please. Here's a close-up of that. This is a really cool plant. I love these tack glands that it has. Very distinctive. The whole genus is neat. Next, please. Okay, this is one that I've had a number of experiences where I've been going along and I will realize, hey, I'm going to see a plant. And this was one of them. I was up on the Cook and Green, I was on the PCT, and I was walking along, and I'm obviously in serpentinite, and I heard the gurgling noise of a stream. I'm going to see this. Went around the corner, found the stream. Sure enough, there they were, the California lady slipper. It's really kind of neat to be able to predict when you're going to see a plant when you haven't even seen it yet. So next. And this, of course, is the, oh, I forgot to put the name on this one. This is the Serpentine columbine at Edgewood. And it grows exigua, yeah. Exemia, that's it. This is interesting. We did have a talk a while back. The difference between this and the Formosa is that this has a longer point, and the hummingbirds, when they come up, this touches a different part of the hummingbird's breast for pollination. And so they bloom at different times. This is later in the season. The Formosa is in the early part of the season, but they also avoid being cross-pollinated by having this structure hit a different part of the hummingbird. So those are ones that you're going to find whenever you have water running through serpentinite in a place where you also have woody plants. They're going to be stuck underneath that. Next. This was one that's a real interesting one. Does anybody know what these flowers are? Yeah, Darlingtonia. And they're in flower.
Is that Butterfly Valley?
No, this is not Butterfly Valley. You'll see that rock there? What does Darlingtonia normally grow in? It grows in serpentinites. This is not a serpentinite, as that white rock shows. This is a trondugemite. Okay. Now, yeah, what a trondugemite is, it looks like a granite, except it has feldspars with no potassium. They're all calcium, sodium, and feldspars. When I was going to this one, I was walking through a normal Sierran woods. I come to the edge of the trondugemite intrusion, trees disappear. Get closer to the center, and you start getting ericaceous plants. So I walked through a whole lining of the road that I was walking on, full of azaleas, and they were all in bloom. And then I got to the center here where it was wet, and here were these Darlingtonias growing. Thanks, Phil. This is the one you told me about. So it was really kind of neat to come up and see one growing in something that is not the typical substrate. By the way, a trondugemite is also related to a tonalite, and we have a tonalite here in the Bay Area. It's Montero Mountain. Yes?
You might explain what the Darlingtonia common name is.
Oh, it's a cobra lily. And there are no leaves. This was too early to see the leaves. They were all flattened down, but it's a carnivorous plant that has two fang-like things with a hood, and it kind of looks like a cobra. It's one of our few carnivorous plants and one of our neatest ones. So next, please. Okay, this is the Bitterroot, and this was taken over on Kite Hill. Normally these grow in serpentinite around our area, but when you get outside of our area, they can grow on any rock that is kind of depauperate, you know, something plants won't normally grow in. The first time I saw this was up in Montana, near the Bitterroot Mountains. It was growing out of a black shale, and you can imagine a big pink bloom of that coming out of the side of a black shale, and there were no leaves left. These leaves had all withered, and it was just big pink blossoms coming out of a cliff. The other place I've seen them that's not serpentinite, you go down to the pinnacles, and they're all over on that igneous rock, which I think has been hydrothermally depleted. So the hot water came through and dissolved out a lot of the salts, leaving them kind of depauperate rocks. They don't have a whole lot of minerals left that the plants need, and this will grow. The one thing this does need is the structure of the rock, and that's it needs fractures to be able to grow down into, because that's what it likes. And here at Kite Hill, the serpentinite is rather, you know, solid pieces, but it has these fractures that it all over that it gets down into and is able to protect itself. Next. And here it is. Where was this picture? Oh, this is up on Mount Diablo, near the top. I found it. And that's what it looks like when it isn't in flower.
Is it Chirp?
No, this is like a greywacke up there. It's, you know, it's not quite shiny enough for a chirp, but it is high silica. Next, please. Our Santa Clara Valley Dudleya. And this one is always found on Serpentonite. Now, the interesting thing is when this was its own species, Sichelii, the Bramsii also grows only on Serpentinites. So they've lumped it in now that it is the Dudleya that grows on Serpentinites is always a Bramsii.
And only in Santa Clara County.
Well, this one's only in Santa Clara, but the other ones are San Luis Obispo and down in Morro Bay, those areas. Next, please. Other Dudleyas aren't so picky, but they do have pickiness about where they get the fractures and so on. This was down in the Santa Lucia Mountains, and this was on marble. I'd been going along for quite some distance and hadn't seen a single one. Came to this marble outcrop, was covered with them. And they're gorgeous ones. They're really interesting looking form. Next one, please. And here's one that was growing out near on the metamorphic rocks near Hetch Hetchy. This is Simosa II. Both of those are Simosa. And this is one thing that drives people nuts about Dudleyas is they can look so different even though they're the same species. The thing I wanted to point out here is the importance of the mosses and lichens and things for the plants to even get started. So they like rock, they like the cracks, but they also need rocks that will have a moss or a lichen or something that they can catch hold of. Hold a little moisture, get that seed started so that they'll have a place to go into the crack and something to keep them alive before they dry out in the first place. Next, please. And this is a really interesting one. This is our unknown, undescribed species down in Little Uvis. Grows in the stream on a block of greenstone. And in that Little Uvis area, that greenstone is just a little section on the road and in the stream. Down the hill a little ways is Serpentonite, and you have Dudleya Sichelii, or Bramsii Sichelii. You go up the road a little ways, and you have regular Simosa. Within 1 mile, you have 3 taxa of Dudleyas.
That's Morgan Hill?
This is not Morgan Hill. This is Little Uvis Road down near.
It's between Morgan Hill and San Jose, west of the two.
Yeah, it's just a very unusual site because not only do you have this there, but on that same greenstone is the next one.
It's the south side of Blair Ranch. You know that.
Yeah, we want to look to find more of these. Is the next one coming? There we go. Is this the Viburnum elliptical that we found down there? And the reason we were looking for that, found this, was because we were taken over there to see Fraxinus dipetala. All in this little area where this greenstone is. It's a funny looking hill. So, is it the rocks? Is it the climate? Next, please. Now we get to a simple thing. This is a madrone that volunteered on my side hill. I live on the Ladera sandstone. Does everybody think that's an easy plant to grow? No. They volunteer. I've already had to remove 4 of these from this hill because I can only have 2. They're huge, they're growing very rapidly, and they're very happy. What is it that I have here that you might not have? The Ladera sandstone is a sandstone, which which means it's going to have an acidic soil because it doesn't have a whole lot of calcium in it. When you have sandstones and low calcium, low magnesium, you don't have anything to neutralize the plant acids, the organic acids that are produced by any living plants. And that's when you start getting this plant and all of its family. Essentially, when you are looking at an ericaceous plant, you're looking at an acid-loving plant. It means it can survive in low potassium, low calcium areas where other plants cannot grow. Remember I said about going into the Trundujumite and running into Western Azalea? Yeah, another ericaceous plant.
Can you give some other examples of ericaceous plants just for
Yeah,
newbies?
Manzanitas, blueberries. Oh, I'll tell you a story that was fun in Lancaster County. Somebody had a blueberry farm in Lancaster County. Well, that's a limestone area. What they had to do to get the blueberries to grow is they had to dump aluminum sulfate on the ground, which produces a pretty good acid. It was the only place I have ever gone to pick blueberries where also poison ivy was coming out through the blueberries. Most of the places you go to pick blueberries, no poison ivy. But because there was limestone there, you had plenty of calcium for the poison ivy, and it wasn't affected that much by the acid. And the blueberries were just barely getting by. I forget how much he had to put on to keep those blueberries alive. It was funny.
Poison ivy or poison oak?
Poison ivy, this was in the east, Lancaster County, Pennsylvania.
Pennsylvania.
Yeah. So next one, please. This is one I like, also a calcium lover. Every time I have come upon this, you have some sort of calcium around, either in the type of rock, usually metamorphics, sometimes marble. It's monument plant. And it's scattered around in the Sierras and up in the Siskiyous. In Colorado, it used to grow to 5 or 6 feet tall. I've never seen one quite that big here. But it is definitely an indicator of calcium-rich rocks. Next, please. This one's a good structure one. These only grow in the foothills in schists that are very vertical. You may have seen those tombstone rocks as you're going through the foothills, where you see rocks sticking up looking like tombstones. Those are the silica-rich layers in this schist. As you got to this location, these would form fractures like that, and this plant would be setting down in those little fractures. I don't think it grows anywhere else except in those metamorphic rocks. Kind of a neat plant. Gets a leaf like this in the spring, and then the leaf dies off and it flowers in the fall with no leaves. Next, please. Our favorite. This likes places where you have landslides broken up, usually greenstones. That's what seems to be its favorite locality to grow. So the soil will be kind of gravelly. You often have a lot of water flowing under. That means the land keeps the landslides going. And with it will grow the next plant. Next slide. You often find this along with it because they both like a similar location. A place where there's water underground, broken up soil, and often greenstone. But another one of these that's interesting is, have you ever noticed that off of Interstate 280 and Page Mill Road, the one corner has this huge amount of this? Well, I got to see a geologic map working at Arastradero, and they mapped that as Monterey Shale, and I went up and looked. It is Monterey Shale. It's looks like porcelainite pieces. And the patch of Aeschylus there matches exactly the outcrop. Now, the Monterey Shale is normally found on the west side of the fault. These little slivers have been broken off through the faults in that area, and this one happens to be there. And I now wonder, I see other patches of Buckeyes in that Stanford Hill area, and I wonder, are those more of these? Maybe it is. Next, please. This is a plant that you don't see very often, the Cyclodenia, and really, or Cyclodenia, I'm sorry. And it's a beautiful plant when you see it. Beautiful flowers. Does anybody have an idea what that's growing in? It is. It's basalt. This is cinder cones. This is up on Mount Harkness in Lassen Volcanic Peak. We actually were not far away from this, but it would have been too much of a hike to go up and look at it. Next, please. And here's another one. Does anybody know what that's growing in?
Chirp.
It's Chirp. Exactly. This is on Snow Mountain. So I put them side by side. I think the next one is a side-by-side picture. No, I wanted to show, here's Snow Mountain. See the chirps? What's the rest of this stuff in here? It's basalts. So you wonder if this is one that's related to basalt or if it's just the structure of the soil. Put them side by side. I think the next one is it. And you see that it's chunky talus, or in this case, cinders. Perhaps it's the size. But underneath this is the influence of basalt. So which one is it? I haven't seen enough of these to know. The next slide shows another one. This was found along Willow Lake when we were out on our field trip this last time. And it wasn't in bloom, but that's what it is. It's one. And you can see this isn't basalt. It's close, but it's more closer to andesite. Once again, it is this talus. So is it the talus, or is it the volcanic rock that it needs? I don't know yet. We have to see more sites. So, next. And there's a flower. Just a very pretty little plant. Next. Anybody know this location? This is San Mateo Canyon, where we have a nice rock garden with Roman zophia here. Yeah, just full of cool stuff. The thing about this is it's greenstone, and the greenstone is very dense, and the water sheets over this, forming these moss layers during the winter, which allow these plants to grow in these mossy, very acidic, very shallow soils. And it really is the texture of the greenstone in this area that causes this. It's just so impermeable to water that the water coming over the edges of it just sheets over it constantly in a continuous flow all winter long. We also have sedum here. It's just a very nice place. And it's got a lot of diversity because it's greenstone, which adds to the minerals that are going to be in here. Next. This one is one that really bothers me, the Erythronium tuolumens. You go up to the location, and it's just this one little section. And then you get to the little curve and little valley, and you go to the next, ends completely. It's all over the place in this one side, and just a little distance over, it stops. Question is this actually due to a difference in the rock type, or is it something to do with the way the plant reproduces? This one does mostly by rhizomatous growth. But it seems over that length of time it would have moved at least a little ways over. Not at all. It just stops. Boom. So it makes me wonder. Is this a rock type? And it's just a small area that has just the right kind of rock?
What's the common name for that? Is it a fawn lily also?
Yes, it's a fawn lily. I don't know if it has a special name. The Tuolumne fawn lily. It's a rare plant. And apparently, you know, rare plants, you have to always wonder, well, why are they rare? Is it the soil type they need, or very special conditions? Next, please. And this is another one that bothers me. This is at Edgewood, and suddenly you get this huge grouping of Piperia elongata. Now, they're more common in this area, but this little patch is just so thick. Why there? And why not somewhere else? Now, one of the things that all the orchids need is they need a fungal partner to grow with. Now, fungal partners, you know, fungi also are sensitive to the conditions in the soil and the minerals that are in it. So maybe this is just an ideal place for that fungi to grow, and therefore you get the Piperias. These are questions I don't know, but you do see these things in the wild, and you just, you know, why here? Next. And this was one that I'm wondering about too. Whenever I find this is candy stick. Whenever I find this on basalt, I see lots of them. There was one location I went to, and it was a basalt flow, and I came around, and there were hundreds of these. I've never seen a patch so good. This one was taken up in Lassen on Prospect Peak, which is a shield volcano of basalt. Now, I have seen this on non-basalts. I've seen it on granite. And the granite ones, I saw one, not very many. So this is one I'm wondering about. Does it like volcanics? Maybe basalts? Maybe igneous rocks? It's a parasite. Maybe it actually has to go with the plant that also grows there. So next. And this one is a rare plant. Has anybody ever seen this? It grows over in Portola State Park. So what restricts it to where it grows? Is it the soil? It's in redwoods, sometimes a little chaparral. But other than that, I did not really see why this should be only in those locations and not somewhere else. Next, please. And this one is beautiful Santa Lucia lupin. When we were hiking up there, it would appear periodically along the road we were walking on. It was my wife and I. And what was interesting about walking on that road is the chaparral would change drastically. You'd have places where it was all ceanothus, and then you'd have another place where it was all something else. You know, it just changed over and over again. And this showed up in one of those. The area turned out to be mostly metamorphic rocks. I had no idea it was metamorphic rocks until I finally, you know, saw the marble up at the end where those Dudleyas are, and realized that there were micas all over the place. And it wasn't sedimentary micas. This is metamorphic rock. So in metamorphic rocks, you can get some very complex things happening. And this is one of those that makes me question. You notice a madrone growing right up above it.
Where did you say that was?
The Santa Lucia Mountains was on the way to Cone Peak. Next, please. Okay, other factors that could take it into account. It isn't all just the rock chemistry. There's also the climatic conditions, the history of disturbance.
History of disturbance.
Huh?
Yeah.
Oh, yeah.
Hilarious.
And other organisms. You know, there are things out there that drive these plants to be what they are. So you have to take all these factors into account, and probably some more, to know why a plant is there. For instance, one of the things you can look at is the mixed soils. What happens when you get to a river? Those are all mixed soils from all the way up the stream. That's why they're good farmland. They're just a mixture. Next, please. I was going to show this. This is the Prospect Fire at Lassen. And you can see the history here is going to be, there are places where it didn't burn, places where it burned, and places where it burned very hot. And you'll notice I'm on Prospect Peak. It didn't burn at all. Why didn't it come up the mountain? Well, because they'd had prescribed burns on that mountain a number of years ago, and it didn't have any fuel to support the fire, so it came up to the edge of Prospect Peak and just dropped to the ground and stopped. So that's a very important history sort of thing. We also have over here, you can see where the devastated zone was, where the landslide came down through here, and the hot volcanic rocks. There's also history here of the lava flows. There are a bunch of small peaks in here, and they have different ages, so the different lava flows have different amounts of weathering that have occurred, so the soil development's different, and you get different plants. Next, please. And other sources of minerals. They don't always come from the rocks below. Volcanic ash can blow in and change it. Think about fish migrations. They found out that most of the phosphorus in the forests of the Pacific Northwest actually get their phosphorus from salmon coming up from the ocean. And then the bear take them out into the woods. And, you know, there are ways of moving minerals around. Dust storms. I saw a thing that said that the Amazon depends on a bunch of phosphorus blowing out of an old lake bed in Africa. Other than that, the phosphorus in the Amazon's pretty much leached out because it rains so much. And then there's humans. Humans move stuff around all the time. I did one study once where I was doing a test for minerals in Colorado. And my section started at a rural highway and went up the slope. And one of the things I was testing for was lead. Boy, right by the highway, I had this huge lead spike. What's that? Well, it's because we had leaded gas, and it was still there. So remember that. When you start moving stuff around, you can disturb a soil which is indicative of that rock. And it may be one that's a rare type. And there may be rare plants depending on it. And you go in and you change that, and you may change it forever. Think about what's happening with the nitrogen being deposited on Coyote Ridge and Edgewood. Plants that are growing there now that were never growing there before because we've moved something in that wasn't there before. And I say that because I think when we do restoration and we do work in the wild, we should think about that. Try to do as little moving around as you can. Try not to make an imprint that might change something that's there. Next, please. And I wanted to say, in final, that California has some very rare rocks. This is a piece of blue schist, and that's Ken Hickman for scale. This is down in Polhemus Canyon. It's one of the biggest blocks I know of free sitting. It's a huge block. And this rock, of course, is indicative of what California is. To make that rock, blue schist, the mineral in it, you have to get it to very, very great depths of about 6 miles or more to get the pressure right. But you can't get the temperature too hot. So 6 miles down, you'd think it'd be pretty hot. Well, the only way you can do this is push the rocks down and then get them back up before they heat up. And we have them here. So, are there any questions? I'll take those. So,
So, you know, you showed a picture of an island with an oak inside of Edgewood.
Right.
And I'm wondering, maybe, you know, like big trees like an oak that's going to put out a lot of leaves over time, that's going to change the geology too in that surrounding, you know, serpentine
it will, you know, start moving the minerals around. And that's why I was showing that kind of, you know, teardrop shape coming down. It will alter it, and, you know, just to get started, though, it had to have some different rocks.
Right.
And then the alteration from biological things is also going to occur. Yeah, it's one of the factors. Yes?
The Santa Teresa hills come down near the intersection of 85, 87, and I've always wondered about the buckeye concentrations in part of the hill right in that area. You know, this is where the greystone came out of the quarries there for Stanford.
Really?
And then there's Jasper and Chirp quarry up a little further. But I think you might take a look there. You'll see them. They're kind of like just a whole bunch of, you know, now white buckeyes amongst the oaks on the side of the hill there. And you brought it home when you talked about the 280.
Yeah.
Yeah.
It's the sort of thing you want to look at when you start seeing that sort of thing. I saw another one somewhere. Yeah.
Do you know what the composition of this fertilizer that they're dropping is fire suppressant?
No, but I heard that it contains a fair bit of phosphate. So, the red stuff.
Well, it's getting a little late, and
Yeah.
you guys may think it's warm in here, so I want to give you an opportunity to buy some books and have some cookies, what's left, but we want to thank Paul.